All right, so if I give you an element or an ion, can you find the electron configuration? If I ask you, hey, give me the shape of the s orbital or the p orbital, can you do that? No? You can't? Well, good. That means I'm actually useful. There's something for me to teach you. All right? I understand. For probably those two targets right now sounded like ma-mwa, 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 ma-mwa. It won't. Believe me, by the middle of the next week, when we come back, you'll understand. All right, here we go. What can the position of the element on the periodic table tell you? How reactive the element is. Alkali, I'm going to stay away from. Alkaline, I'm going to respect. Halogens, I'm going to be very afraid of and run away from. Noble gases, with the exception of radon, which is radioactive, I am not going to be as concerned because it's a noble gas. Kelsey, it's not going to react with anything. Actually, if you were to say, hey, breathe in some xenon, I would go, do I have to? I mean, I don't want to breathe in xenon. She goes, yes, you must, or else, yeah, I'll kill you or something. I go, okay, all right, fine. I breathe in some xenon, and then something very interesting happens. When I start talking like this, like my son. It's the opposite. Xenon is a gas. First of all, because it is a noble gas, it's not going to react with anything in my lungs.
Can we get to that?
No. Okay, because it's rare, and it's going to be very expensive, and you're not worth it. All right, so when you breathe it out, it causes your voice box to really expand because it's such a big atom. As it comes out, it pushes your voice box apart. And the more room you have as the air escapes, the lower the pitch. So you're going to sound like this. Even girls will sound like this. Now the opposite is helium. If you were to breathe that in, helium is so teeny tiny that as it comes out, it does not let your voice box open up very much. The smaller the opening, the higher the pitch. So we all will sound like Mickey Mouse if you were to breathe in some helium. Okay? If you were to breathe in some fluorine, like that, you would die. Because just one step over to the left, and you are dealing with elements that are extremely dangerous.
Is helium poisonous now?
Helium is not poisonous. What happens is if you breathe enough of it, then you won't be breathing oxygen. So people pass out if they play around with helium too much. Not realizing that it's not the helium that is hurting you, it's the fact that you're breathing so much helium in, you're not breathing enough oxygen. So you pass out. Yes?
Isn't it that like some of the noble gases actually use neon lights and they run electricity through them?
Yes. Yes. We'll talk more about that later.
What does ammonium do when you swallow it?
Ammonia or ammonium?
Ammonia.
Ammonia is highly reactive. It's a base, so it's like swallowing the opposite of acids.
Doesn't it like bubble in your throat? That makes it a big
It'll damage your throat really bad. What is it about an element that makes it reactive? How many electrons it has in the outer shell. Remember your biology teacher talking about outer shells? Or your middle school teachers?
Yes.
Well,
one kid remembers.
what is a shell? A shell is an electrons can be thought of as existing in shells or layers around the nucleus. Kind of like onions have different layers. Well, electrons live in those layers. What? Shrek. Yes, yeah. Somebody in first period commented about Shrek. So I guess if Shrek was an atom, then all the different layers where Shrek has, you would have electrons in those layers. I like to think of those layers as kind of like neighborhoods. You know how you have Scarborough and Emory Heights and Briarcliff. Those would be the energy levels. I'm sorry, the energy shells. What is another name for these energy shells? Energy levels. I gave it away. Energy levels. And how many energy levels do elements have? Well, it depends on which period it lives in. If it's period 1, it will have 1 energy level. Period 2 will have 2 energy levels. Let's see if you can see the pattern. Period 3 will have 3. Period 4, 4. Period 5, 5. Okay, I think you get the pattern. So let's try some of these. Find lithium on the periodic table. Yes. The answer to 38 is depends on the period number.
No, sorry, 38.
38 is depends on the period number. Okay, so for example, lithium. Find lithium on the periodic table. Spencer, which period is it in? So how many energy levels does it have? Let me get some white ink. 2. Zirconium. Gracie. Find zirconium. Which period is it in? So how many energy levels? Lead. Nicoli. Yes, 6. Uranium. Hunter. 7. Chlorine. Riker. 3. What are subshells? Subshells, okay, so if energy levels are neighborhoods, subshells would be houses. Houses. Areas within energy levels, that should be within energy levels where electrons live. So, neighborhoods or subdivisions, as Isaac said, would be energy levels. Houses would be the subshells. Subshells. How many subshells are there? Actually, no. There are 4. There are basically 4 types of houses. And we here in Oak Ridge, we can relate to this because at one time there were only, 6 or 7 different houses. There was A, B, C, D, E, F, G, H maybe, depending. So the higher you went up the alphabet, the bigger the house was. But there was just a few different models. That's it. And you can still see that, especially Woodland. Have you seen Woodland? You know, some of those old houses, it's just, you can still see kind of like the same format. Okay? Why could we never expect to see an electron? Because in order to see anything, can you see anything in the dark? No. In order to see anything, you have to have light. Good. In order to see anything, you have to have light coming off of it. You have to give it light and have light coming off of it. All right? Microscopes work on the same principle. In order to see these teeny tiny little things, you have to shine light on it and it reflects it back. Well, the deal about electrons is if you shine light on them, then they disappear. It's like they're extremely shy, and as soon as you give them any kind of energy, they're gone. They're gone. You can still see in the dark because even in the dark, things are giving off light. That's why cats can see in the dark. Okay? They absorb energy, and then that energy is released in the form of infrared. All warm bodies can give off infrared light. So, think of electrons as things that are extremely shy, and when you give them energy, they go away. Actually, if you think about it, this is just a cop-out. The fact is, we can never see an electron. We've never been able to see an electron. So the theory is that the reason why we can't see an electron is because when you hit them with energy, they go away. This is actually, there's a name for this. And I've been told that on Breaking Bad, he refers to himself as Heisenberg.
Yes.
Heisenberg's uncertainty principle is what states this. If you've seen Back to the Future, Dr. Brown refers to Heisenberg's uncertainty principle as well.
I can't
Never seen it. Why would I want to see a show where the chemistry teacher is the bad guy?
He's a meth. He's not a bad guy. He's dying.
I don't care. Just because, okay, trust me, if I ever find out I'm dying, I'm not going to make meth and allow people to get hooked up on meth. That's evil. That is evil, evil, evil. I don't care what you guys say.
Watch the first, it's just a TV show. Watch the first episode and then see, and tell me what you think.
Does he make meth?
Yeah.
Then he's evil. I'm sorry.
No, but he stops.
After he made meth. After he dies, he stops.
But he makes the best meth and the best meth.
Oh my gosh, have you seen what meth does to people?
Yeah.
He's evil. What do we call this whole theory? It's called the quantum theory. The quantum theory.
Why I knew that, I have no idea.
Quantum theory. And that's a word that slipped into our vocabulary. There's a Bond movie, The Quantum Solace. The Quantum Solace. In Star Trek, there's quantum torpedoes, which I don't think have anything to do with the quantum. The quantum theory is basically a mathematical model that tries to explain where these electrons are. I don't understand the quantum theory. Actually, some of the people who created the quantum theory says it's hard to understand because it doesn't make any sense.
Oh, wow.
I mean, they actually said that. And that encourages people to go out and try to understand the quantum theory.
We're like, let's go, guys.
So, what does this model predict next? The existence of orbitals. Okay? So, if energy levels are neighborhoods or subdivisions, and subshells are houses, what would orbitals be? Bedrooms. Good. Bedrooms.
Kitchen.
Areas within subshells where electrons live, kind of like rooms. If subshells are houses and energy levels are neighborhoods.
Feel it.
Hello, I'm Hank Green. Welcome to Crash Course Chemistry. Last time we left off with Mendeleev believing he had discovered a cosmic mystic reality about the world, but in fact, he had discovered the effects of his worst enemy, tiny, invisible particles. Electrons, which are so marvelous and peculiar that it wasn't until 80 years after Mendeleev's first periodic table that they were really understood by anyone, and to this day, still very, very few people understand them. Before quantum mechanics, scientists envisioned the atomic world as just a miniature macroscopic world. Electrons seemed to just be particles orbiting around a nucleus. In fact, there was a great Dane, other kind of Dane, Niels Bohr, yes. Like certain other people I might name, he sometimes felt like he was in the shadow of his older, more successful brother, an Olympic soccer player, while Niels's handwriting was so poor that he had to dictate his PhD thesis to his mom. Nevertheless, he was an ingenious physicist. Now, you might remember a couple episodes back when John Dalton determined that elements only exist in discrete packets of matter. Well, by Bohr's time, the same thing was known for the energy given off by electrons. That energy only came off in what ended up being called quanta, which is the root of the term quantum mechanics. In 1913, Niels Bohr came up with a simple model for describing these energy levels for a single electron in hydrogen, merely assuming circular orbits. So there is some truth to the framework of thinking of electrons as particles. However, when he or anyone else tried to apply this to more complicated atoms, they failed miserably. Long story short, electrons don't really behave like particles. They're better described as waves. So we've known for like 50 years that this is an entirely inaccurate way of visualizing an atom. Nuclei, yeah, you can think of them as solid particles, but not electrons. Electrons are wave-particle dualities. Now it is time to move a little bit into the realm of metaphor here, because I'm going to tell you how I think how I think of electron shells and orbitals, not really how they are. The music of electrons is not simple music. It's no three-chord song. It's like Beethoven, but with more rules. Hard, fast rules that can't be broken. In that way, at least, it's more science than art. Electrons exist in orbitals, a bit like the individual notes on a keyboard. But the orbital's tone isn't complete until it has 2 electrons in it. And orbitals exist in shells. The first shell just has a single orbital, an s orbital, which can only fit 2 electrons. That's why the first row of our periodic table only has 2 elements. They play a simple song, those two, and a song that every other element will build upon. The second electron shell, though, is physically larger and thus can include more than just the s orbital. A second sort of orbital with 3 different configurations is added, the p orbital. Instead of just being a single tone, the p orbital is more like a 3-part harmony, with 2 electrons in each part for a total of 6. Those 6 electrons of the p orbital plus the 2 s electrons are the 8 electrons referred to in the octet rule, the desire for most of the lighter elements to have 8 electrons in their outer shell, just like a musical scale. This is often described in terms of fullness or satiation, as if the atoms are like devouring electrons, but I prefer to think of an incomplete electron configuration as a cacophonous symphony playing at different keys and different tempos. And the closer you are to harmony, the worse it is, until one final note chimes in, that 8th note, and everything crisps into full resolution. A deep, complex tone emerges and the atom settles into complete harmony. The harmony of the noble gases. That's just how I think of it. And just like with music, there's a bit of notation to learn as well. It's important to know how to write out what we call electron configurations, a condensed way of showing exactly where all of an atom's electrons are. First, we write the number of the shell, then the letter of the orbital, then the number of electrons in that orbital, and repeat until we run out of electrons. So for hydrogen, with just 1 electron, it's 1s1. For fluorine, it's 1s2, 2s2, 2p5. So if we're trying to understand reality, we should not think of electrons as circling around the nucleus of an atom like planets around a star, but instead as an excitation around the nucleus. And the shape of that excitation is the orbital. Orbitals are precisely the reason that everything exists. They are the root and the key and the nexus and the crux and the keystone and every other metaphor of not just chemistry, but existence.
So, if you can figure out how the electrons are arranged around the nucleus, then you can figure out how an atom's going to act. You can figure out its personality. So today what we're going to do is focus in on figuring that out. Every electron lives in a certain spot around the nucleus. There's a way of basically telling the person that you're communicating with where that spot is. And it's very similar to the metaphor that we used on last Friday, 8 days ago, that has to do with kind of being like a dormitory where students live in different types of rooms, the sauna rooms, the patio rooms, the den rooms, the fountain rooms. All right, yes?
I can't see.
Did you try opening your eyes? Are those your glasses?
No, like I can't see like the projector.
Okay. You may need to see an optometrist.
No, like I can't. Like unless I do this.
Oh, because, oh.
Right, because
All right, then why don't you switch over there with sit next to Emily.
Permanently?
Sit behind Emily permanently. Okay. According to the model, if you could see the s orbital, which you can't because we're not actually sure that electrons exist, let alone that they really do live in these types of rooms. But if you could, and we use the model because it works, what would it look like? It would look like a sphere. A sphere. A sphere. So the electrons, and there's going to be 2 electrons living in this room, would be spinning around, doing their electron thing, so that if you were to look at it, it would look like a cloud that looks spherical. And I don't know why, but chemistry teachers think this is terribly important, even though we're not even sure that electrons exist. If we could see p orbitals, what would they look like? Well, you've played around in gym with dumbbells, right, Devon? You guys work out a lot in football. You know what dumbbells look like. Well, they think that what's going on is that electrons are the two electrons are spinning around like this. So the p orbital looks dumbbell shaped. Dumbbell shaped. Dumbbell shaped. So, do you remember back 8 days ago? How many students could live in the sauna room? 2 students could live in the sauna room. That's right. And because every room, the maximum occupancy was 2. How many students could live in the P rooms? And 2 per room. Do you remember how many total rooms there were? There was 3. Okay, so there is 1 sauna room, 3 P rooms. So 3 times 2 students each. Gracie, do you need a calculator? No. 3 times 2 is 6. Excellent. And there does seem to be 4 in between those, right? How many students can live in the D? Let's see. S had 1 room. P had 3 rooms. D will have how many rooms? Follow the pattern. 5. So, if you have 5 rooms, 2 people each, how many total students can live in the D rooms? 10. How many students can live in the F room?
14.
Okay, how many F rooms are there going to be? 1, 3, 5, 7. You had 2, 6, 10. What separates these guys? And this is going to be 14. So there is a pattern to all this. How many sublevels are there? In other words, sublevels are the types of rooms. How many sublevels are in the first energy level? First floor had how many students? How many types of rooms?
4.
No. If you remember from back 8 days ago. Types. There was just a sauna room. Yeah.
Oh.
So for a total of 2 students. So in the whole first floor of the electron dormitory, only 2 students can live. Because I remember, if you remember, there was a cafeteria right next to it.
Yeah.
All right. How many can live? Oops. How many can live in the second energy level? Let's see. The first energy level had 1, which is 2. How many rooms are in the second energy level? There's a pattern.
3.
Okay. First floor had 1 type of room. Second floor will have 2 types of rooms. S and P. Since S can hold 2, how many can P hold?
6.
Remember, 1 room, 3 rooms, for a total of 6 students. So, how many total number of students can live in the second floor? 8. Follow the pattern. The third floor will have how many types of rooms? S. Second type, P, and there are 6 students there. Third type, D, with how many rooms? 5, for a total of? So how many students can live in the D section, in the third floor? Total of 18. What's next? 4th floor. How many types of rooms will the 4th floor have?
4.
S, P, D, and F. 1 type of room. 1 room for a total of 3 rooms for a total of 5 rooms for a total of 7 rooms for a total of total number of students that can live in the 4th floor?
32.
34. Oh, no. Okay.
Use a calculator if you need to.
I'm gonna do that.
32. Believe it or not, your periodic table, take out your periodic tables. Oh, I forgot to tell you, every day in chemistry, you should have 2 things out. Periodic table and calculator. All right. Don't write anything until I tell you, but notice that there is, on the periodic table, a section of 2, right? Then over here, count them. 1, 2, 3, 4, 5, 6. What section is that, I wonder? How about this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Holy moly! Get it? Holy moly. It's mole week. Here's something you can write down in order to help you. This is the S section of the dormitories. This is the P. This will be the what? D. And the F. 2 little notes that you may want to have right below the sodium here. The D rooms are 1 floor behind. F's are 2 floors behind. Okay? Remember talking about this a week and a half ago when we were talking about the fact that UT Medical Complex, the 3 buildings there don't correspond in their floors?
Yeah.
Okay? That's kind of like what I'm talking about here. So in order to get to the 3rd floor D section, this right here, you have to go to the 4th floor sauna. All right, so don't write this down, but this is the pattern. 1S, 2S, what's this going to be? No, we're by floors. 3, 4, 5, 6, 7. So over here is the 2nd floor P section. 3rd floor S. 3rd floor P. 4th floor S. Now we come to the D section, but this D section is going to be found in the 3rd floor D section.
So would it be 4D?
No. Well, below it would be 4D. Yes. Over here would be 4P, 5S, 4D, 5P. Now, draw solid lines, something to get your attention right here. And then an arrow down and an arrow down. That needs to tell you that when you get to that section of the dormitory, you have to take an elevator to go to the F section. Which F section is this? If you're in the 6th floor, and then you go back here to the 5D, 6P, 7s down to the
5s,
up to the
60.
So the whole periodic table can be thought of as a giant dormitory where the boxes do not refer to the rooms, the boxes refer to students. So knowing this, let me erase all this because we're just going to start with the information that we have on our periodic tables. Knowing this, we can find the address for all the electrons for every element. Let's begin with sodium. All right, let me show you how this is done. Very easy. First of all, imagine helium is right here. And if you do, the first two, we have 11 electrons to place. The first two go in the first floor sauna rooms. 1s superscript 2. That's 2 electrons. 9 more to go. No p section. See? No p actually, imagine that's over there. No p section for the first floor. Second floor, sauna room, 2 students. Second floor, patio rooms. There are 1, 2, 3, 4, 5, 6. We have now placed 10 students. We have to place the 11th one. The 11th one will live in the 3rd floor sauna room, and I only place a 1 there because there's only 1 student there, the sodium student. And that is the electron configuration for sodium. All right, I need somebody to help me with the electron configuration for chlorine. Right here. Let me erase all this. There are 17 students to place, so we have to find the address for all 17. Who would like to volunteer? All right, Jeffrey, let me erase this so that you don't copy. Because could you? Yes. It follows the same pattern. It keeps building on itself. So yes, we could have continued on from there, but let's start in the beginning. Go.
So it starts out as 1s2.
1s2.
And go down as 2s2.
2s2.
And then 2p6.
2p6. 2 plus 2 plus 6 is 10. We got to go to 17. Continue on.
And then 3s2.
3s2.
3p5.
3p5. 17 electrons. 17 students. And we know each one's exact location. That is called electron configuration. And you use the periodic table to guide you through it. All right, Kelsey, thank you for volunteering for the next one. Let's make it a little harder because people are only now beginning to kind of see the pattern. After we do this several more times, they're going to see the pattern. I want you to go to one of my favorite elements, iron, right there. All right, let's start back here, gang, with the very first floor. Kelsey, where do those 2 electrons go? 1s2.
And then 2s2.
2s2.
And
2p6.
3s2.
3s2.
3p6.
3p6.
4s2.
4s2. Hunter, welcome. Warning, warning, warning. Okay, because now we're in the D section, and what do we know about D section? Okay, so if you're in the 4th floor, you're really in the Very nice. All right. Kelsey's got the pattern. She's got the pattern. Dun, 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 dun. She's got the pattern. Dun, 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 dun. That's a bit of a stretch, isn't it? Okay. Selenium. No, let's go one down to tellurium. Is that right? Tellurium. Yeah, tellurium. All right, Emily, you want to try it? Okay. Devon! Hey, he's after that interception, he can do this. You had an interception and what else? They called your name a couple more times. Fumble recovery?
No, I forced a fumble without getting recovered.
Oh, okay. So in other words, you had a bigger game than your brother. He just tormented people. He just scared people. You actually did something, right? All right, here we go, gang. Got a long ways to go. Short time to get there. Let's go.
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and 5p4.
Holy moly! Devon's figured it out. Okay. Any questions so far? There's got to be questions. No? Nicole wants to do one. Okay, Nicole.
Did it get any more complicated?
Oh, yeah. Let's see. Let's go right cheer. Samarium. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, Nicole. This is it. This is your time to shine. Starting with. Let me erase all this or else you can cheat. Okay, go.
Okay, 1s2.
Good start.
2s2. 2p6. 3s2. 3p6.
So far, so good.
4s2.
Okay, danger, danger, danger.
So 3d10.
Out of danger.
4p6.
Danger, danger, danger.
5s2. 4.
Out of danger.
5.
Danger, danger, danger.
6.
Okay, here's the critical part. What comes next? We're not in the D section. We are in the... So you have to follow the arrows down here. So this is... Yes. Nicole, that was awesome. Good job. All right. This is as Serenity, then you can do the next one, since you actually understand. All right, this, Nicole, this is as hard as I can make these. And actually, you probably won't see one this hard on a quiz or a test.
So a quiz, you're just gonna give us like.
When we get this big, I'll show you a different way of doing it. Okay? But you need to be able to do this way.
So we can't have a quiz over this way.
Oh yes, you'll have a quiz over this way.
Okay.
Okay? But you probably won't get one this hard. Seaborgium is number 1, 2, 3, 4. Wow. Seaborgium, named after an actual Oak Ridger, Seaborg, Glenn Seaborg. All right, start one step at a time. Come on.
You erased the
P.
Yeah.
Now you'll be able to do it. Which floor? We've already finished the one. We're in the second floor. That's okay. Danger. How about 3D10? Oh, dyslexic one. D310. You got all the numbers right and the letter, but not in the right order. Let's try it again. Let's see. P4. P4. All right. Let's try it. 4P6. Good. Danger. You already did 4P6, my dear. Danger, danger, big danger, big danger. Okay, you should see arrows going down. Hush. Danger, danger, danger. Back there. Which D? 6D. Serenity. I'm sorry, I can't do anything harder than that. You did it. Good job. Wow, that was long. She just found the locations of every one of the 106 electrons of Seaborgium. 106 electrons she found rooms for.
Good job.
All right, but as you can imagine, this could get really time-consuming. So we usually use the full electron configuration for the smaller elements. For the larger elements, we use the condensed electron configuration. It is a shortcut to all this, using the noble gases as a, well, I'll show you. Write this down. Let me tell you a story. Well, it's not really a story, it's more like an anecdote. Has anyone ever gone down to Florida for the summer? Yes, yes, good. Best part about going down to Florida is coming back up through the great state of Georgia, right? You can't drive down to Florida and drive back without going through Georgia. It's impossible. Okay? As you're going through Georgia, you start seeing some signs on the side of the road. At first, you ignore the signs if you're the dad because you probably can't afford, after spending all the money in Florida, you can't afford those things. But then the signs begin to wear you down. And the children begin to wear you down. Dad, can we have some? Please, Dad, can we have some? And then you start thinking about their hairy, juicy deliciousness.
What? Kiwis. Coconut.
Yes, Georgia kiwis.
Coconut.
Georgia peaches. During the summer, you go up and you begin to see the signs. Georgia peach fuzzy. That's right. Fuzzy goodness, sweet goodness. So you buy a box and you tell your kids that you're not going to eat any of them until you get through Georgia. It's our reward for getting through this very long, boring state. But by the time you get to Atlanta, now you can smell them, and your mouth is always watering. So you start eating them, and you yum, eat all the fuzziness, and then you eat the juicy sweetness, and then you crack a tooth on the pit. It's called a pit. And the pit, you throw away the pit, right? That's what you do. You throw it away because you don't need the pit. You can't eat the pit. You can't even chew the pit. It is a very hard piece of material, so you throw it away and allow prisoners to cut down the little peach trees that can be found all throughout the highway going up north through Georgia, right? You realize there are peach trees up and down I-40, I-75 that prisoners have to cut down because people eat the peaches and throw away the pit, which is what the peach tree wanted to do in the first place, right? For the peach tree, the pit is the most important part. For us, the juicy, fuzzy goodness is the most important part, right? Okay? So, in the same way, the pit in electron configuration is made up of electrons that really don't do anything. They just sit there. They do not ever get lost. They do not get gained. They just sit there. So, when we're doing the electron configurations for these guys, what we do is we find the noble gas. Now think, noble gases complete the sequence, don't they? Helium, neon, argon, krypton, xenon, radon. And they haven't named that one. They complete the sequence, so they're the perfect choice to use as a pit. So if we have to go to lead, which is, I think, right here, what you do is, instead of saying 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f. Am I right? Oh, no, I'm not. That's it. That's it. Instead of saying all that, we say xenon. You like that?
Yes.
That's the electron configuration for xenon. Agreed? Because you have to be able to do it the long way and the short way. Okay? That is the electron configuration for xenon. Agreed? Agreed. And those electrons never get lost or gained. So they're not really important. So why can't we just symbolize them with the element xenon and then continue from there? That is condensed electron configuration. Find the noble gas that is up and to the right, the noble gas that's inside, and then continue from there. 6s2, 4f14, 5D10, 6P2. That is called condensed electron configuration. All right, let's Hunter. How about if you do chromium? This one right here. So what you do, don't write this down on your periodic table, but arrow up, and where do you start? What is the noble gas that's inside? The pit is argon. This is chromium. This is lead. Argon, and then you start right there. You didn't go all the way over here. 3D4.
Why is PVXE?
Because you're going to learn from Xenon.
Up and over. Xenon.
Oh, my bad. I was looking at a different one.
Bromine is right here. Benny Ben. Do bromine for us.
I don't know who that is.
Right here.
Oh, you don't know.
Yep. Is there another Benny Ben?
Oh, I didn't know who that was.
That was you.
But Mr. Moreno, bromine's next to krypton. On mine.
You're right. You're right. Sorry. Bromine is right here. So, Benny, up and over. What do we begin with?
So AR.
Yes.
4S2.
Yes.
And 3D10.
Yes.
4D5.
Yes. Betty, nice. With a big B for Benny. Yes.
So is it going to be a way that we have to do it, or can we get paid either way?
No, I will ask you for full electron configuration or for condensed. Usually if it's a big element like uranium, I'll ask you for condensed. If it's a smaller one, I'll ask you for the full. But you need to be prepared to do a big full one too, if I ask. Yes, Serenity.
Where do you go with the words on the bottom?
Okay, let's do that one. Let's see, someone who's not contributed. Emmy, thank you for volunteering. I love you all's volunteering spirit. All right, so uranium is the third one here. So, gotta go up there, right? And then there, and then there. Okay. Now we're here. We're being dyslexic. Floor. What's the number that's there? 7. S2. Okay, and now we come down here. What? 5. F3.
Wait, so they all going to read them?
Yes. And all of these would go to Xenon.
Oh, okay.
Another way of doing it would be if I ask you for gadolinium, that would be number 60. What's the noble gas closest to it and inside of it? That would be number 54.
Oh.
So if you're number 60, then the noble gas would be the closest noble gas to it, but inside of it, which would be 54. No. So if I ask you for, let's say, xenon, you can't say, oh, xenon in brackets. No, you would have to go krypton and then start from there.
Oh wow.
Okay?
So how do you go? I thought you were supposed to go right.
No, you go up and right.
But you can't go right.
You can't just go right.
Please go up.
Because remember, using the analogy, then the pit would be outside of the fruit. You understand? Okay? No, the pit is always inside the fruit. You got to get through the fruit in order to get. Or here's one that you might be able to relate to: a blow pop. The gum is the noble gas. Okay? You can't just have the gum outside and then you get through the gum and get to the candy inside.
That'd be hard.
It would be hard.
Can I just like melt the stuff around the gum?
Nope. How can you determine? Okay, so I taught you a long, drawn-out thing, the electron configuration. And then I taught you the shortcut to that. Do you know there's a shortcut to the shortcut?
I like that.
That's
like
crazy.
lies.
Do you have to go right in it?
No. No, actually, if you can count to 8, then you can do this. Can you count to 8?
Yeah.
Oh, then you can do this.
3, 5.
Actually,
I can only count.
the most important electrons, the electrons that give you your personality, are the S and P electrons. The electrons that are in the outermost S and the outermost P. The one beyond the pit, beyond the noble gas, are the most important electrons. Okay? Since they're only found in the S and P, there can only be a total of 8 of them. So you do not include the D or the F section. You do not include the D or the F section when you're counting these things. All right. Zach. Oh, Isaac. Yes. Okay. 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 Isaac, Mr. W is going to be delayed by a few minutes to call him if you need him from Mr. Jackson's room. All right. So, why are these so important? Because they're the ones who are the farthest away from the nucleus. They're the ones who are the most likely to get lost or gained. They are the fuzzy, sweet, peachy goodness of the atom. So they're the ones who are most likely to be eaten. Not the D's, not the F's, it's the S and P electrons. The S and P electrons. How do we do this? Quite simple. Where are they on the periodic table? Okay, all we care about is the S and P electrons, right? So where are they on this periodic table? And that's how you solve these questions. So this is S1, S2. We don't care about the D's. P1, P2, and we'll finish here tomorrow. Okay, so let's look at the outer shell electrons for these guys. Remember that all you care about are the S all you care about are the S and P's. If you're in the D section, we don't care about any of those electrons. If you're in the F section, We do not care about any of those electrons. So, let's find calcium. Calci. 1, 2, right? 1, but that's 3. 4, 2, but that's 4. S2, P2 is 4 total of electrons, right? S2P3 would be 5. S2P4 is 6. S2P5 is 7. S2P6 is 8. So, calci, this is really as easy as just finding where calcium is and determining how many, what column it's in. So calcium would be, so calcium has 2 outer shell electrons. What does that mean? Everyone wants to have 8. That is the goal. 8 is great. Calcium has all of argons plus 2 more. So what do you think it's going to want to do if given a chance? Drop 2. Give up those 2, as Nicole said. That's correct. Okay, but we're getting a little bit ahead. For now, we're just figuring out how many electrons. The number has to be between 1 and 8. All right, next up is tin. Jeffrey, how many outer shell electrons does tin have? 4 total. 2 in the S, 2 in the P, so tin is 4. Remember, it's the S and P electrons. Hunter, radon. 8. Does that make sense? Radon is a noble gas. It doesn't need anything or anybody. Why? It's got 8. It's full. It's completely full. All the S, all the P, full. Aluminum, Ben moles.
Yeah.
How many outer shell electrons? 3. Fluorine. Spencer. 7. Very good. Next. Potassium. Devon. 1. Serenity. Molybdenum, which is somewhere around here. You get the hard one. How many S and P electrons does it have? Let's do the electron configuration. Okay, so up and over krypton. Krypton, then starting right here. What? Five S2. Good. How many S and P electrons does it have? S and P.
I thought it was 3.
How many S and P electrons does it have? Gang, the secret to all transition metals and even the non-transition metals is that how many S and P? It won't have any P's. You haven't gotten there yet. So how many S electrons will it have? 2. So it doesn't matter who you are over here. How many outer shell electrons will all these guys have? 2. How about platinum? Right here, Serenity. 2. Thorium. Thorium, Emmy. Thorium. 2. So if you're in the transition or the inner transition areas, your outer shell electrons is 2, because you haven't gotten to the p section yet. Remember, it's only the s and p electrons. The number has to be between 1 and 8. Any questions? What makes an atom stable? What do they all want?
8 electrons.
8 electrons. They want to have 8. They want a full S and a full P because that completes their outer floor. Remember the metaphor? What happened if you were a resident assistant and all your floors were completely full? You got $1,000. That's right. You got $1,000. So you're liable to trade, right? Get rid of students or gain them in order to get the full configuration. So how does an ion affect electron configuration? Well, if you are like halogens that have 7, you are desperate to gain an extra electron. So you are likely to become an ion. You are likely to become an ion by gaining. If you're an alkali, if you're something like potassium, you're going to want to lose electrons so that you can have the 8. Everyone is willing to lose or gain electrons in order to have the 8. Because 8 is great. So, when you're doing the electron configuration for these guys, you have to either lose or gain electrons. Now, that means you're going to have to go back and remember what -2 means. -2 in every other subject will mean take away 2 things. Not in chemistry. Because remember, in chemistry you can only add or take away electrons. So -2 means you have added 2 negative things. A +2 means you've taken away 2 negative things. All right, let's do it. Spencer, give me the electron configuration for bromine, and then give it to me for bromine -1. Condensed. Condensed. What noble gas is up and to the right? What? Okay, so let's begin with argon. Oops. Argon, continue from there. Okay, let's go back to the periodic table. All right, so we are right here with bromine, and this is argon. So 1, 2, 3, 4. What section are you in? This is actually the S section, my friend. S, P, D, F. All right, so go 4S. 4S. How many electrons do you have in the S section there? 2. Now we're here. Do you remember what's so special about the D section? Okay, so it's
3D.
yes, and not all the way, but close.
5P.
I think we're in the 4th floor, my friend.
4P5.
4P5. Oh, a little dyslexic moment there. Okay, good, Spencer. That is the electron configuration for bromine. But think about it. What does it want to do in life? How close is it? Who is its hero? Krypton is its hero. How close is it to becoming krypton? So, when bromine becomes -1, what happens to this 4p5? It becomes? Very good. So a -1 means you get to add an electron. -2 means you get to add 2 electrons. So they will add or take away electrons in order to become like a noble gas. Tanaya, now that you know what that looks like, you can do calcium. First of all, give it to me without it being +2. Up and over to the right to find the noble gas. Argon. Now start right there. After argon. 4s2. Next. Oh, that's it, right? 4s2. Okay, good. Now, make it calcium +2. Okay. What does +2 mean? That means you've taken away 2 electrons. Good. Okay. Well, take away 2 electrons. Yes. Is it now like a noble gas? Yes. Who is its hero? Its hero is the closest noble gas, argon. Now, is it like its hero? Yeah. Isaac, potassium +1. Mm-hmm. Now, make it potassium +1. Is potassium now like a noble gas? Good. Randy, sulfur -2. Good. You're in the 3s. What? How many electrons are there? 3s2. And now we're right here. You're in the 3rd floor. 2p is up here. 3p. 4. Okay, but this is not sulfur. This is sulfur -2. Look at it. How close is it to becoming like a noble gas? So what does it have to do? Okay, take away 2, and now you are at 3p2.
Well, I meant -2, so it'd be adding.
Add 2, and you are at 3p6. See how this works, folks? I mean, think about it. Right here, potassium. Potassium is a shiny, soft metal. If you had a piece like a Tic Tac piece, and you were to put it in your mouth, you would first hear a sizzle, and then you would hear a pop, and then a small roar. And then you would see pieces of your tongue and your teeth coming out. Why? Look at this. How close is potassium to becoming like argon? It is desperate. What does it desperately want to do? It desperately wants to give away that 1 electron. Now that potassium has given up that electron, now it's like, I feel better now. Thank you. So now potassium +1 is something that's in our foods. Look at your food. See how many potassiums are on there. Potassium nitrate, potassium chloride. Okay, that is potassium +1. It has given its electron. Now it's happy. Now it's happy. Because now it feels like it's like a noble gas. Over here, bromine. You see a brown liquid. And Emily starts saying, Mr. Moreno, drink that. That looks like fun. Drink it. Drink it. And I'm looking at it and it says halogen on it. And I go, Why? Because I know that all halogens are one electron away. One electron away from becoming like a noble gas. What does that mean to me? That sucker's dangerous. It's going to hurt me. It gives me an electron, or it takes away an electron, and it changes the way my water works, and I'm mostly water. So I'm going to say to Emily, no thank you, I'm not going to drink this bromine. Now, what if I was to introduce something like sodium that wants to give away an electron? They react, blah, 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 blah. Now it's a white crystal. Now I'm more likely to reach in there, take that white crystal, put it in my mouth. I'm probably still not going to do it without investigating the properties of sodium bromide, but I'm more likely to do it because I know that sodium has given up its electron, so now it's happy, and bromine has taken an electron, so now it's happy. They're both happy. So I know that they're not as dangerous as they were. 10, last one. Emmy, have you done one? All right, Emmy. Up and over. Which F2? What? 5S2. Very good. Now, if it was plain old tin, she would have said 5p2. Well, tin has to lose 2 electrons. That's what plus 2 means. Where's it going to lose it from? Well, it has the S rooms full. It has the D rooms full. What's the only thing that's not full? It's not even close. P. And colleges do not like for there to be rooms that are empty. So if you're going to lose 2 electrons, you got to lose it from the top floor. And here's a case, Emmy, and every once in a while I'll give you one of these. Here's a case where it really doesn't become like a noble gas, but it gets closer. It gets closer. Now it's only 2 away. That is why tin plus 4 is a more popular ion than tin plus 2. Because when it's tin plus 4, then it does lose all the S and P electrons, and it becomes like krypton. Except it has the D section, but the D section's full, so that's okay. All right? Questions? Then let's finish this. What makes alkaline metals so reactive? What makes them so dangerous? They are how many electrons away from becoming a noble gas? 1 or 2. They are 1 or 2 electrons away from becoming like a noble gas. So, as you can imagine, they are desperate. They can smell it. They can smell noble gassiness. Why are the halogens so dangerous to us? They are 1 away, Hunter. Very good. They are 1 away. If they were just to gain 1 more electron, then they would become like a noble gas. All right, who can guess what the final question's answer is? 68. Why do the noble gases not react? They have the 8. That's it. That's what they want. They have the 8. So if you come up to me, Emily, and say, hey, breathe in this...
Chloroform.
No, breathe in this krypton, xenon, radon. I'll say, okay, I'll breathe in the krypton and the xenon. I won't breathe in the radon because it is radioactive. But I'll breathe them all in if I have to. Why? They're safe. They're not going to do anything to me.